Good morning. We are almost at the end of this, and for this morning session, there will be a new chair, Sam Xie from Clarkson University, who chaired the session. He's a PhD student at Clarkson University. I will let you in his hands.
Thank you, Louis, and welcome back. And our first talk is given by Alan, and he's going to talk about the Terwilliger algebra of tournaments. And Alan, it's yours.
Okay, thank you. So first, let me begin by thanking the organizing committee for the CRM workshop and also this thematic program here at CRM. I've enjoyed a lot of the talks online, and fortunately, I was able to be here in person. So for at least the last week of it, I'm going to talk about the Terwilliger algebras of tournaments. So these are our subconstituent algebra version, and the tournaments are a type of rank 3 scheme that is more precisely called doubly regular tournaments. So non-symmetric rank 3 association scheme. And the interesting thing about these is that there's only one type of algebra that occurs. But as we'll see, there's many non-combinatorially isomorphic versions of it. And so there's lots and lots of tournaments, and classification of tournaments is ongoing. So there's lots and lots of these schemes. And this is a follow-up to a talk that I gave in Wisconsin in 2019, which was the last time I left home. And so I'm assuming that you remember everything from this talk, but I'll remind you what the key points were. So we had done I had a student, undergraduate research student, in the summer of 2019 that was doing calculations of these Terwilliger algebras for these rank 3 cases, and we had calculated everything up to dimension 27, and we found certain patterns that were occurring all the time that we couldn't really explain. So these were the questions. First of all, if you pick any vertex X, and for these DRTs, I'll call them, the combinatorial isomorphism groups are very small usually. There are not that many that have transitive automorphism groups. And so you get many Terwilliger algebras. But no matter which vertex we picked, we were always getting a multiple of 4 plus 9 for the dimension of the Terwilliger algebra. Okay, we're just computing these things on gap. As I said, the association schemes were up to dimension 27, so we could do this pretty quickly. And we were analyzing the dimension of the irreducible modules, which again we could compute with gap using central idempotent calculations and calculating the span of T multiplied by these central idempotents, and show that the dimension was only 3 for the principal module, which it has to be, but everything else was dimension 1 or 2. And so again, we didn't have a good explanation for that. And the other strange thing that we found is that many of our non-combinatorially isomorphic schemes we were getting the same complex Terwilliger algebra. So isomorphic Terwilliger algebras for different schemes. Not only that, for every vertex, they're isomorphic. So then that got me looking at the rational Terwilliger algebra. So here in this talk, I'm introducing this as just to remind myself that the coefficients are rational. I'll just call it QTX. So you take the generators of the Terwilliger algebra, which is some collection of 0-1 matrices that sum to J, where you've partitioned off the diagonal. And for the other ones, you take the non-trivial adjacency matrices that are in your scheme. And then you represent the algebra that you generate with those over the rationals. Okay, now since the entries of these generators are all 0-1, you get rational structure constants for the basis that you have. And so you have this rational Terwilliger algebra. It's closed under transpose, and so it's going to be semi-simple as a rational algebra. And in every case that we had tried at that time, the rational Terwilliger algebra distinguished the schemes.
Are you saying coherent closure, or are you telling us it's always a coherent closure?
It's not coherent.
Okay, if you have a 0-1 basis,
0, 1 matrix basis is closed under transpose and hence conjugate transpose. And so it's a semi-simple rational algebra.
But the entire Terwilliger algebra has a 0, 1 basis.
As a 0, 1 generating set.
Oh, generating set, okay.
But the structure constants of the basis you'll get will be rational numbers. So you have a rational Terwilliger algebra. At the time, this was the, forgive Bill, he wasn't at the previous talk.
It wasn't the first part.
So the rational Terwilliger algebra was distinguishing the algebras. Okay, and so now we're fast forward to the next conference, 2022. Now we do have answers to the first two of these questions, which are sort of answers that you'd expect. I'll explain those in a second. And we've completed the order 27 case, which gives us motivation that part 3 is working. There's also some work on Terwilliger algebras for non-symmetric schemes. I know people who do P and Q polynomial are really focused on symmetric association schemes, but there are some results, mostly constructive, for non-symmetric schemes. And in some sense, this rank 3 case is the first meaningful example of a concrete calculation of these. And so we can build from this in the future, I hope. Okay, so that's the outline, and just follow along the numbers because I've got the slides numbered. Okay, so quick review of rank 3 association schemes. I've got an association scheme where one of the non-trivial elements is not symmetric. So that means A transpose has to be in the also an element of the also an adjacency matrix that's giving me the scheme. And in this case, I'm rank 3, so that's A and A transpose are the only non-identity elements. And then what happens? Well, A times A transpose is the result is that when you multiply A times A transpose, you have to get the valency. So that's this K, in this case is the valency of A. You have to get that as the coefficient of your identity. And because A times A transpose is symmetric, the other coefficients have to match. So the coefficient of A has to match the coefficient of A transpose. And A plus A transpose is J minus I. So you end up with an identity like this. The valency of A times A transpose, the valency is a character, so it has to be, and the valency of A matches the valency of A transpose. You get that K squared, which is the valency of this, has to be the valency of the other side here, which is K plus 2Ku. And so you get that K is 2U plus 1. So that means the scheme has order 2U plus 1 plus 2U plus 1 plus 1. So that's 4U plus 3. To make the regular condition work on intersection matrices, you get that A squared is U times A plus U plus 1 times A transpose. And from the spectrum of the intersection matrix, you can calculate the eigenvalues of your element A, and that gives you the character table. You complete that calculation, you get the character table. Now, I'll just mention that the character table for this matches the character table of the conference matrices. The only difference with the conference matrices that Jason Williford was talking about earlier last week is that you don't have this plus 1 here, and you don't have the minus in front of the order. So very, very similar breakdown in this structure. And in fact, a lot of the theory is sort of parallel to that of conference matrices, as you'll see. Okay, now when do these exist? This is an interesting problem that's related to the existence of skew-Hadamard matrices rather directly, because if you take your matrix A that's in my scheme and you append it by putting a 1 in the first column and a 1 in the 0 column and a 0 row, you get an n times u plus 1 order matrix that is skew-Hadamard. So there's a direct connection between these and the skew-Hadamard matrices. The standard table algebra, so by table algebra, I mean just the algebra generated by the matrices without any reference to the vertices. All you need for the algebra is the character table. So this character table makes perfectly good sense as an algebra under pointwise multiplication if you just take the columns as your basis. So this always exists. The association scheme, in that sense, you have to represent this now as this three-dimensional algebra as n by n matrices with 0, 1 entries, and that's much harder. So you have to find these skew Hadamard matrices of order n+1, and those aren't classified for lots of orders. So as I mentioned, there were quite a few that we had calculated of order 27. They start to be non-Schurian at order 15, and then 19, 23. I think the numbers are 2, and then 4, and then 23, I think. And then you get a blow up, 373 of order 27, which were those are the ones we had calculated in our calculations. And just in the fall of 2019, just before I gave my talk in Wisconsin, Hadi Karagani's group, which included Thea Rezavehi and Mohammad Madian, had classified skew Hadamard matrices of order 32. And then they had joined up with Hanaki to extend that to schemes of order 31, and they found 98,300 exactly of these association schemes of order 31 that are non-symmetric, rank 3. For order 35, they're still not known. That's again the last I saw people, so they could have been solved in the meantime, but I haven't heard yet. Now, for orders larger than 35, they're known to exist when n is prime. That's just the Paley tournament. For the Paley tournament, you take the cyclic group of prime order P, and you sort it with the identity, and then all of the squares mod P of your power of your generator, and your non-squares. Now, since it's 4 mod 3 minus 1 is not a square, and so you get two elements which are permuted by the inverse when you invert the group elements in the list. So when you add those up, you get an A, which is not symmetric, and it's when you invert all the elements in the list, you get the A transpose. Okay, so these are the Paley tournaments. They always exist when n is prime, and for other orders, they're known to exist all the way up to order 275, which would be the case where my U is 68. They're not known to exist for that, for U equals 68. And again, this is the last time I checked. So please correct me if that's wrong. Okay, so we're interested in talking about the Terwilliger algebras of these matrices. So let me quickly define the Terwilliger algebras that I need. We've seen this definition a lot. So take an association scheme with these adjacency matrices. Chris Godslaw was asking me if the scheme is commutative, and I don't care. So all this has to be is a homogeneous coherent configuration where you add up all of these. It gives you well-defined intersection matrices, and it sums to J. Okay, and then you take any vertex you want, and you look at the row in your adjacency matrix that corresponds to that vertex X. You take that row and you write it as a diagonal matrix, so for you this way, and make that your EI of X. Okay, and for letting your I run from 0 to D, you add those generators. So these generators E0 through ED will sum to the identity, and then you throw in all of the non-identity adjacency matrices that came from your association scheme, and that's the Terwilliger algebra. Now, if you can use these EI stars to define the A star matrices. Of course, when it's P polynomial, then just one A star matrix will do. Anyway, there's a question about that will come later, so let me not foreshadow that. And it works perfectly well if you do this over the rationals, because you have a 0-1 matrix basis and you multiply everything out, everything's going to be rational, and so you'll have rational structure constants of the algebra. So you have a complex Terwilliger algebra, which I just called T, and the rational Terwilliger algebra is called QT. Now, both of these are semi-simple, and that's again because the algebra is closed under it's a sub-algebra of Mn that's closed under transpose, and in characteristic 0. And you can ask the same question over finite fields, and actually there's a recent paper by Hanaki that does this, which characterizes when they're semi-simple. So he has a paper on modular Terwilliger algebras, and when they're, and it addresses the question of whether they're semi-simple or not. Okay, I think it's the first treatment, I think, of the modular case. So that's nice. Now, general, you can vary the matrix, you can vary the vertex X. So every time you have one of these association schemes, you get a list of n Terwilliger algebras for each ground field. So if you think of this as an invariant for the combinatorial structure, you really have n different components of this invariant. And so you're interested in, if I give you a scheme, you can give me n distinct Terwilliger algebras, and we can ask, is the collection really different or not? Okay, and so that's the spirit of this question. So just to review the calculations sort of in detail, what my NSERC summer student and I did was to compute all of these Terwilligers for everything up to order 27. At the time, we didn't know the ones of order 31. And so this is basically everything at the time. And always we found the dimension was 4 times something plus 9. The 9 comes from the principal module. And so everything else was adding up to a multiple of 4. And the non-primaries that we found, we could calculate their dimensions in the complex case. When we worked over, to do that, we work over splitting field. I'll explain that in a second. They all had dimension 1 or 2, and up to order 23, the complex Terwilliger algebras was enough. Now, I shouldn't say there's just one. For every, I think in almost all cases, they always had one Terwilliger algebra of maximal dimension, with just very few exceptions. But you needed to look at the whole list, which dimensions showed up, and the list of dimensions for each of these is different for order up to 23. But for order 27, we get huge families, which are where you get the same list of Terwilliger algebras. The dimensions of the Terwilliger algebras, even the dimensions of their centers, match exactly in many cases. So complex representation theory is not enough to distinguish the order 27 ones. And fortunately for me, I'm a rational representation theorist. I work over the rationals. So this is a good problem for me. So here's the questions that following that summer that we were left with, and that I decided I would try to address for this conference. So we want to know about the dimension of the Terwilliger algebra. Is always a multiple 4 plus 9. Can we bound it? Okay, this is something we didn't try to do before, but it seemed that the data we were getting was telling us we probably could. Our non-primary reducibles, we want to prove that they had dimension 1 or 2. And then can you distinguish with the rational Terwilliger algebra? And in particular, is it actually, can we finish the calculation of this problem for order 27? Okay. Now I say here with the exception of thin schemes. So Terwilliger's in Terwilliger's original papers on the subconstituent algebra, you can see that for groups, the Terwilliger algebra is just a single matrix algebra whose dimension is the dimension of the scheme. And so any two groups of the same order will give you the same. And even over the rationals, that's true. That's something that I'll show you. So that has no chance for thin schemes, but for others, it's something I wanted to address. Now, also when you have a student, you hope that they first look at the existing literature and learn it well. So when I came back to this question, the first place to look, which would inspire us, would be the subconstituent algebras of the strongly regular graphs. For that, there's a paper by Tomiyama and Yamasaki that characterizes the Terwilliger algebras for strongly regular graphs. And the way it worked was it used an idea from this Cameron Gödel-Seidel paper. So I'll be a bit nostalgic here because Muramasa talked about this paper, Terwilliger talked about this paper, Bill talked about this paper. This is the name of this paper is strongly regular graphs that have strongly regular subconstituents. Okay, and the result that comes out of it that most people were talking about was the dual triple product identity that's derived from it. But the way the main theorem of the paper works is when you have a strongly regular graph, so this A1 is our adjacent matrix of a strongly regular graph with eigenvalues K, R, and S, then they establish this matrix identity. And this just uses the structure constants of the association scheme to get. And then you analyze this at the subconstituent level. So at the subconstituent level, so I break off I put X in the first position, and this is the X subconstituent. So I have the first row and the first column is just a vector, okay? And the E will be in the first row of A1. Once you've sorted things, you have all the ones go in that component, and then this B1 subconstituent is the block that's sort of underneath it. Okay, so if K is the K1 is the valency of A1, this B1 is going to be a K1 by K1 block matrix, and the B2 will be n minus K1 minus 1 by n minus K1 minus 1. Okay, and the other sizes are sort of implied. Now, when you analyze this identity, subconstituent by subconstituent, you get lots of other small identities involving the B1s, the N, and the B2. Good, everybody knows how to do this because you've done this many times. Okay, and then Tomiyama and Yamazaki, in deducing the Terwilliger algebra for the strongly regular graph, eigenvectors for B1. Okay, now in the first identities, you can see that the all ones eigenvector will be an eigenvector for B1. So you can sort that out. So you can take an eigenvector that's orthogonal to the all ones vector for B1, and then analyze what happens. So when it's orthogonal to E1, then it's also going to have the property that J times that vector will be 0. And so you get from these identities here, here, and here, and here, you get reductions for B1 times that vector and B1n times that vector, and etc. Okay, so this is how that works. And from that, they deduced that B1, N, and N transpose, N, B2, N transpose have the same eigenspaces, and same for the ones in the bottom corner. And also they could count the one-dimensional irreducibles. Now, I'm sure that Paul is listening online, maybe, and he would have analyzed this very in depth and found and got the idea to show then that the irreducible TX modules are thin. So that is E1 star T, E1 star is one-dimensional, or excuse me, commutative, and so it's irreducible or one-dimensional. So that's the thin concept, and certainly in Paul's papers they have that. Okay, and that instantly, because the diameter of those modules is not the full dimension, it's not 3, so they have to be dimension 1 or 2, and so it's just 1 if they only occur in one of the EI, T, EI star blocks, and 2 if they occur in both. And there's a nice eigenvalue, eigenvector property that Tomiyama and Yamazaki established for telling when they're in both or when they're in just one. Okay, so we'll follow that same approach. Establish a matrix identity for your distance doubly regular tournament. Decompose into subconstituents. Here we don't get this for free, but the B1 subconstituent will be diagonalizable because we only have one generator of the A generates the algebra. When you analyze this subconstituent, you know that the B1 that's there is J for its size block, minus the I for its size block minus B1. So you can write B, because you know that I plus A transpose is J, then you also get that in the subconstituent. So that's really helpful. In fact, that's crucial to have B1 diagonalizable. Again, we get a bunch of matrix identities from the subconstituent analysis. Okay, and again, you get that when you put in this one here, this one and this one, when you put an eigenvector, so the all ones eigenvector will be an eigenvector for n, and so it's also going to be one for for B1. If I have an eigenvector of B1 that is orthogonal to J, orthogonal to E, then it'll also be, you'll also get identities involving it from these, from this first four. Okay, and that will tell you that J times that vector is 0, and so you get information from the next subconstituent identities. From that, you can show that B1 n times J minus n transpose, so basically n times n transpose, and n B2 J minus n transpose will have the same eigenspaces, so they all commute. Okay, and that's enough to show that the E1T, E1 star component subalgebra, which is part of the Pierce decomposition of this space, is commutative. For E2 star, E2 is commutative, and therefore your Terwilliger algebra will be thin. And that's what you need to show that the dimension of the non-primary irreducibles is 1 or 2. So it's the same approach. Works. And now to extract more information, like Tomiyama and Yamazaki did, we take an eigenvector that has the eigenvalue r or r bar. And what you show then is that n times that eigenvector is actually going to be 0. And so that allows you to take the eigenvector for B1 and insert it into the bigger matrix so that you get an eigenvector for A and A transpose. And so you get an irreducible T module of dimension 1 that only occurs in either the B1 component or the B2 component, depending on which one you picked. Everything else, you have that n transpose V is an eigenvector for B2, and so you can build a two-dimensional space that will become an irreducible T module. So either for B1 or B2. Now, for the 4K plus 4L plus 9 result, here we use the fact that the decomposition, the B1 and B2 have the same size. And the R and the R bar are complex conjugate eigenvalues if they occur. And so since B1 is a rational matrix, if R occurs as an eigenvalue, so will R bar. So they come in complex conjugate pairs. And because you have this if you diagonalize B1, which you can do because you can, if you diagonalize B1, you'll get a certain number of R and R bar eigenvalues, depending on the multiplicity of those irreducibles, and then a certain number of two-dimensional pieces that are matched in the B2 part. So the dimension of the two-dimensional part in both has to match, because you know that each of, if it occurs here, it's thin, and it also occurs there when it's two-dimensional, so that size will match. And so if you get some R's, you also get some R's for B2. So they don't just come in complex conjugate pairs, they come in sets of 4. Now, since the modules themselves will be isomorphic, if the eigenvalue is R, and it only matters if it's in the B1 component, B2 component, you get 4. If you get an eigenvalue R, then you also have an R bar for B1, you have an R for B2, and an R bar for an R bar for B2. So you get a set of 4, and that's all the one-dimensionals that you can have. No matter what their multiplicity is, you can always only get 0 or 4 of them. And since the dimension of T is the sum of the squares of its irreducible dimensions, then you'll have 4 plus something with some multiple of 2 squares plus the primary, which is 4K plus 9. So you get that. The only way you can get a maximal dimension is that all of the non-primary components of the B2 diagonalization are in dimension 2 modules. And in that case, you get 4 times 2u plus 9. Interesting enough, though, that actually occurs. So the Paley tournament, it seems, has always maximal dimension. So in my order 27 cases, the maximal dimension is 57. And that's the biggest one. It almost always occurs. There's a few where it doesn't occur, but it occurs for the Paley tournament, and all of the TXs for the Paley tournament will have that.
This K can depend on X. Different X's can be
Yeah. In the largest families, and there are quite a few of them, there are 5 different dimensions of Terwilliger algebras that occur in the list of when you sort through all of the vertices. Paul, did you have a question? Your camera came on.
His microphone on.
Okay. I think your microphone's not on, Paul.
So far, so good.
Okay. Okay. And now for the rational theory. So there's a ring theory argument that I can give to show something, and this is now in my language, rational representation theory language, that thin irreducible T modules will have rational sure index 1. What does that mean? If T is your semi-simple algebra, okay, and let's make it a Terwilliger algebra. I'm gonna write it as CT because I need a few fields here. You'll have your primary component, other components. So these will have say their dimension n, and this will depend on which irreducible you have. I think V is what I was using for irreducibles. And now for the rational Terwilliger algebra, if you analyze what Paul has shown in his subconstituent papers, you'll see that the primary module is thin, and it's generated by the x hat vector, which has a 1 just in if we sort things in the first position. Now, when the basis of your irreducible module is realized by rational elements with rational entries, it's called realizable over the rationals. And in that case, so in general here, if I go below, below this one, there will be an irreducible module of QTX such that when I tensor up with C, it's involved here. So, but this is a rational algebra, and being a semi-simple algebra, all you can say is that it's a matrix ring over some division algebra whose center is a finite extension of Q. So this is some M, I'll call it R, of Q adjoin the field of character values of this V, okay, where the character values come from this module. Okay, so this will be, oh, I shouldn't even put that here. This is a division algebra, and the center of this division algebra is this field of character values. Take the basis of the Terwilliger algebra and extend by all of the values of irreducible characters that you can get on this. That's what this field is. This only works in characteristic 0, by the way. It's a property of semi-simple algebras in characteristic 0. Now, when you tensor up, what can happen is to get rid of this division, eventually when you keep tensoring, this division algebra will get smaller and smaller. The splitting field is a maximal subfield of this division algebra, and there could be quite a few. So if I take the splitting field, so this is a maximal, I take a maximal subfield of this division algebra, that still doesn't have to be a Galois extension. I have to go to its Galois closure before I get to a Galois splitting field. So let K be my Galois splitting field. Now, because this one is realized over, the first one, the primary module is realized over Q. So actually this division algebra isn't even there. Here, what will happen is for this field doesn't have to be Galois. So it embeds it has many embeddings into its Galois closure. So when I go to this splitting field, I will get my dimension from above as the matrix dimension, okay? But the number of ways I can embed this is the number of embeddings of the field into its Galois closure. So I actually get a whole bunch of simple Galois conjugate modules at this level, and there's one for each Galois extension. Okay, so that's how this works. Okay, now to say that this has sure index 1 means that over the rationals, this is a matrix ring over the field of character values. Division algebra goes away. That's what it means. So in order to decide, since my irreducible modules in my non-symmetric rank 3 case are always thin, in order to decide if they're isomorphic or not when they have the same matrix. So when the complex Terwilliger algebra is isomorphic, all of those matrix dimensions above are the same. I can't distinguish. So even when I vary X through the entire list, I can match them up exactly. I can't distinguish. When I go to the rationals, then I'm getting matrix rings over fields because they're all thin. When I take the center, I get the direct sum of these fields. So I have to distinguish these fields. Okay, now the way we can do this with gap is we take a basis of the center of the algebra, and we have to order the basis in such a way that you have the identity first, your A contribution second in the original basis of T, okay, and then everything else. Now, when you take a basis of the center of the algebra, what gap is doing is taking what's called the Casimir operator on this basis. It calculates the center using the Casimir operator. The image of that is a theorem that the image of that is an ideal of the center. And so when you throw in 1, it will make that well, and it has to do a little bit more checking, but it will give you the whole center. And that's what gap is doing. So the image of A, because the original scheme is generated by A, you can ask if the image of A will generate the algebra. In these cases, and this is something my program checks, it always does. So I pick up the minimal polynomials that generate those fields from looking at the second element of my basis that gap gives me. And I analyze then those fields. When they don't match, I have to check if I have a root of one minimal polynomial in the other field. And so I can distinguish the centers. The number of degree 1s doesn't distinguish, but the degree 2 extensions, the number of them doesn't distinguish, but the actual fields themselves distinguish the algebras. And sometimes I have to go to dimension 4 to do that. I should say that these fields that I'm getting in these cases for these non-symmetric rank 3 are quite wild. And they don't have abelian Galois groups. And what they do have, and this is something I can't explain, they do have usually Galois groups that are Coxeter groups of type B. So they're Reith products of an elementary abelian 2 group with a full symmetric group. Invariably, that's what they are. So we've done this for all of the DRTs of order 27, all 373 of them. The rational theory is enough. And if anyone's really ambitious and wants to try this, it takes 5 days to calculate the 373 ones. So I'm probably not going to try the 98,300 of them. Okay, I've only got 3 minutes left. I want to say a little bit about Terwilliger algebras in general of non-symmetric schemes. Terwilliger had done some basic theory, and given the Terwilliger algebra of G when G is thin, so that's any finite group, commutative or not, this is the same thing. And since then, people had started looking at constructions. So the Terwilliger algebra of the tensor product of 2 association schemes was done by Hanaki and some of his group. And they also got formulas for Terwilliger algebras of Reith products with complete graphs and thin schemes. So G means a thin scheme. Anyway, if someone wants to know about Reith products, I'll let you know what they are. The algebra is quite easy to write down. It's just a fusion of, it's a particular fusion of the tensor product. Okay, there's a result by Tanaka, which I'm not sure people have noticed. It's if you have a commutative association scheme whose non-primary irreducible modules all have dimension 1, then you can characterize those schemes. They're Reith products of complete graphs with thin schemes. And I should mention Bangtang Chu has extended this to the varietal, what he calls the varietal Terwilliger algebra, which is like the generalized Terwilliger algebra, for those of you who know about those things. There's Ki-Jung Kim, one of the people that Hanaki was working with, extended this to Reith products of a scheme. So if you know the Terwilliger algebra of A, there's a Reith product with quasi-thin, or 3 equivalents. 3 equivalents is when all of the non-trivial elements have valency 3. And after that, Musachuk worked with Chu to give a formula for the Reith product in general. This is not in the Reith product version, it's just, you just have two components. So the Terwilliger algebra A tensor with the Terwilliger algebra B, but here there's 5 components of the formula. So I didn't write them down. And you can ask certain things about that build on this. So I have a paper recently about the symmetric square. So that's something you can ask. I don't think any people have looked at. So there's also work by Xu on this generalized Reith product, or what Xu calls a wedge direct product, which is another construction of schemes that uses a scheme homomorphism instead of a tensor product. So it's sort of like a way to do extensions of schemes. If you like symmetric, you can ask any of these questions for ordinary graphs. So take the Terwilliger algebra graph, which is not necessarily regular. You can do this, and I'll just close with something for the mathematical physicist. We do know that the DRTs contain many type 2 matrices. And I think various people have calculated these and perhaps even classified them. I'm not sure. But type 3, I don't know. But it was hinted at this that Munamasa maybe knows. For the non-symmetric, rank 3 came up in his lecture, but he didn't really give us an example of a generalized spin model that comes from a DRT. And perhaps people know this. So I'll end with that question. That would be something that people are interested in here, and I'll stop there.
Are there any questions?
Can you so can you tell us this
Wedge direct?
This X box, sorry, yeah. This box with an X imply what is that?
So it's a type of extension. So the way I think of it is this. So you have your B scheme here and your A scheme here, and you have a homomorphism of schemes that goes between them.
Okay.
And then on the tensor product, you can redefine a product, which is a twisted product. And what you can create out of this is this wedge direct product, which you can think of as, if you have the kernel of psi here, then these parts match, okay, and the co-kernel would be here. So you can think of this as an extension in 2 ways. It's the kernel of psi extended non-trivially by B, or the image of A extended by the co-kernel. So the image of A is a quotient scheme of A modulo its kernel. And this twisted product basically tells you the information you need to do the extension.
One more question, very naive. So in the Terwilliger theory, modules are thin if you've got dimension 1, and sometimes we say the Terwilliger algebra is thin if all these things have dimension 1. But in the sort of Zhisheng theory, thin means all the valencies are 1. Is there any connection between the two, or are you using the two?
I'm using both. Yeah.
Using both.
So a thin scheme is a group.
So thin, you're right. Thin scheme is a group, and quasi-thin is
A thin Terwilliger algebra means irreducibles are thin.
Okay. I just wanted to make sure that
it's exclusive.
both.
Sorry. Yeah.
Thank you.
The questions? Okay, let's thank Alan again.